Okay, hello, we're Team Cybotz, Team 21351, and I'm Anya.
Uh, my name's Arya.
My name's Arjun.
And we're doing a presentation on the advanced odometry mechanisms and their comparisons. Okay, so in this presentation, we're going to talk about hardware, software, and our findings. So a little bit about us is that we're a fourth-year team, and we won awards at both the regional and state level. And in this presentation, we compared multiple different methods of localization that we tested in the past season, and we collected data for you guys so you could figure out which method of localization would be best suited for your bot. So first, what is odometry? Odometry is the use of sensors to track the robot's relative position on the field. And for many teams, they use it in autonomous for consistent and accurate movements. So now we're going to go into the hardware. So the first topic is wheel-based odometry. And there are four types of wheel-based odometry: two-wheel plus IMU, three-wheel plus IMU, and pinpoint. And the odometry pods track the dead wheel's rotations based on the wheel's circumference and translates those rotations into linear distance traveled. And this works because when, for example, if a bot is pushed up against the wall, the motorized wheels will still run, but the dead wheels will stop, which means the robot will know it has stopped. Okay, the first method is two-wheel plus IMU, and basically there's one pod for the translational, one for the lateral, and the IMU tracks the location or the angle of the robot. And in our personal experience, this was really good for simplicity, but it was less accurate and consistent compared to other methods of odometry. The next method is three-wheel, and basically in this one, there's two parallel wheels and one perpendicular wheel. But in this method, we saw there was a lot of wheel slippage in the robot. The next method is three-wheel plus IMU, and again, there's two parallel pods and one perpendicular pod, but the IMU also is accounted for in the angle of the robot. And in our personal experience, the IMU actually helped make the heading more accurate. And this is a comparison of a two-wheel versus a three-wheel layout of the robot. And as you can see in the three-wheel, there are two parallel wheels, and for the heading, we calculate the difference between them. And the last method is the pinpoint computer. And the pinpoint computer takes in data from two odometry pods, the lateral and the translational, and it fuses it with the IMU ratings. And this is, in our personal experience, we found this to be the most accurate out of all the methods. And it also has a faster refresh rate compared to the other ones. And the last one is the optical tracking odometry sensor. And this is unique compared to the other methods we saw because it actually uses lasers to track the relative position of the robot in the field. And for example, this works kind of like a computer mouse. And in our personal experience, we found this to be really compact. So if you guys have a small robot, it might be a lot to put 3 dead wheels, but this is just a small chip. And we also found this to be really fast, but it was somewhat inaccurate over complicated paths such as sharp turns. And this is a cost comparison of all the wheels of the methods of odometry and their cost and their parts. And this is just a small comparison of the methods of odometry and their accuracy setup, pros and cons. Okay. Next, we're going to go into software.
So now we've learned like the hardware component of incorporating odometry into your robot, right? And so the next part is how do we take the data and what do we do with it and how do we essentially use it to get the robot to move? And that's where the software comes in. So briefly, there's various different types of software that you can be using in order to get your robot moving. The most common, the most heard of are custom PID algorithms like point-to-points. Those are, you have to build them from scratch. There aren't any like known libraries for those that you can clone the quick start for and get working on it. Then there's the pure pursuit algorithm. It is a bit different than your traditional PID. It does have like curves that PIDs point-to-points don't have. And then That's also, you do have to build custom from scratch. And then there's Roadrunner 1.0, and then there's Pedropathing 2.0. 2.0, they just released a new version this past week, actually. And those two are actually ready to use libraries. They're the most, feasible for most teams to start odometry. So those are the only ones that we're going to be going over. And this is just like a quick overview. I'm going to pause here a bit so you guys can like grasp this information and just understand all of them. All right, so okay, wait, I see someone taking a photo. Hold on. Okay, so moving on, Roadrunner, we're gonna go over some math here. You really don't have to worry about math, especially when it comes to Roadrunner and Pedropathing. You never really get to touch it. It's mostly an automatic tuning process that has its own documentation for it. So Roadrunner, it is a trajectory generator and a follower, and it does generate smooth time parameterized paths. But I want you guys to think about Roadrunner this way. Roadrunner is, think of a GPS. When you plug in your final destination, what it will do is it will pre-calculate the route, and then it will tell you the directions to go there. But what Roadrunner does is it uses quintic Hermite splines. So it takes in six data points. It takes in your start position, your end position, your velocity at the start and end, and then your acceleration at the start and end, and then it solves a 6x6 matrix to create this little path. This is an example path, but an example path that you see over here, it's called a spline. And essentially, since this is pre-computed, you cannot change this when your robot is running. So that is one downside of Roadrunner. It will guarantee you time. It will efficiently, it will give you a prediction of time. So it's very consistent in that way, but it does not have reactability. So if you were to, if you wanted to incorporate another sensor input into your autonomous, camera input or something like that, you won't be able to do that because it has already pre-planned the path. And so obviously, to make it easier for you guys to code your autonomous paths, there is a visualizer for Runner. It's called Meep. This actually, it's a Java-based simulator, so you do have to like actually download it into your project. There are docs for it, so it's really not that hard. But the key features is it lets you change your robot's constraints. So your acceleration component, your deceleration component, your size and width of your robot. It does provide you an accurate time taken for your path. So when you code a path and you're visualizing it, it will give you the time that it will take for your robot to travel that entire path. And it helps you just essentially visualize your trajectories and be able to know where the robot's going to go and basically have them all out before you deploy to your robot. And essentially that's just easier because deploying to your robot takes a while, and you don't want to sit through 3 hours of work when you could do it in maybe like an hour and a half. Okay, so moving on to Pedropathing. Pedropathing is actually new. It was released last year, and they just released a new version, like I mentioned. It is a path generator and a follower, and it doesn't use quintic Hermite splines. It does use Bezier curves, which are a bit different in theory, and they are also continuous, so you don't have sudden jerky movements between your paths. And essentially, taking on the GPS analogy that I used before, what Pedropathing is, you give your final destination, and it will compute your path to there, your directions. But what will happen is Pedropathing, say with the GPS, some traffic comes up, there's an accident, there's a roadblock, something like that. It will your GPS will reroute you. That's essentially what Pedropathing does. If you tell it you want it to detect for something, like an obstacle, or the robot just not moving or something like that, it will you do have the ability to change the path in real time, because every control loop, it is checking where the robot is and where it needs to go, as compared to Roadrunner, which pre-computes the path. So that is one benefit of Pedropathing. And yeah, it uses 4 corrective vector calculations. So if your robot deviates off course, it uses 4 corrective vectors. It's a combination of your forward vector, so points along the path with target velocity, your lateral vector, so if your robot drifts sideways, it will pull it back, and your heading vector, which is the angle that your orientation of your robot. And the fourth one is the centripetal force vector, and this one actually Roadrunner does not have. So if you're doing sharp turns and the momentum of your robot is carrying, making you overshoot your desired state, then the centripetal vector will account for that. And this is the visualizer for petropathing. It is a web-based simulator, so you don't really have to like download anything into your existing project. And the benefit of this is that you really don't have to like code manually for the trajectories to pop up on your field. You can just drag and drop points, and then it will auto generate the code for you. So that's the difference between petropathing's visualizer and Niji. And then this is a like pros and cons list of Roadrunner and petropathing. You can see over here, the Roadrunner does have its own built-in command base. It's called actions. But the downside of having that is that in autonomous, it does not have the support to use any third-party command base that you want to use, like say Next FTC, FTC lib, solvers lib, anything like that, or Mercurial. Petropathing does though, because it does not come native with any command base library. So yeah, and petropathing, it does have it's sensor fusion friendly. So if you wanted to, process some camera input and then change your robot's trajectory based on that petropathing, it's very, very easy to incorporate that in petropathing compared to Roadrunner. And then just the compatibility comparison. So out of the localizers that we talked about, the only one that isn't compatible across both of them, or just across Roadrunner, is 3 plus IMU. It's pretty self-explanatory, I feel. And findings now.
Okay, so now based on all of what was just said, we collected some data, and this is what we found. So in this video of the path, this is a video of the path that we instructed the robot to execute, and as you can see, it's a pretty harsh path with lots of heading changes and sudden turns. So the different localizers were subjected to a lot of abuse, just as they would have been in a competition. And we collected data from this, which we'll present on the next slide. So here's just a quick chart. You can see all the different methods of localizers as columns, and the rows are the different traits that we tracked. So we have the amount of error in inches per run. Then we have the consistency and loop times. Consistency is simply the percentage of times that the robot performs to our expectations. And our expectations were defined as within acceptable parameters. So as if the robot's error was within 3 degrees of heading, within 1 inch in the x direction, and within 1 inch on the y direction, then we classified that as a good run, which counted towards a higher accuracy. Next, we have loop times. Loop times is simply the amount of time it takes the robot to finish one instructional loop. The times you see are in milliseconds. So I'll let this sink in for a moment. So now we have a graph. This graph simply shows us how the different methods of localization fared when it came to the heading error. So on the y-axis, you can see our dependent variable, which is the accumulated error in degrees. And on the x-axis, you can see our independent variable, which was the run number. So for example, on run number 2, there is approximately 3.75 degrees of heading error for the optical tracking sensor. So I'll let you guys look at this for a moment. Next, we have the same exact thing, except this time, instead of tracking the amount of error in the heading direction, this is for the amount of error in the x direction. The units are in inches. Same drill. This time, the dependent variable is the amount of error in the y direction. And so that concludes all of the data we found. And we do have some team updates though. So we're going to release a website that's going to turn the game manual that's released this afternoon into an interactive quiz where you guys can compete with each other and learn the game manual in a fun and interactive way. And we will also have detailed CAD videos for everything you need on how to learn 3D modeling, so be on the lookout for that as well. Any questions?